Welcome, everyone, to another journey with the All Sorts podcast, The Deep Dive.
Yeah.
Today, we're diving headfirst into, well, the biggest scales imaginable. Think black holes, galaxies, their whole cosmic dance.
It's a fascinating topic.
Absolutely. Especially for you, our learner, seeking knowledge that's quick, thorough, and full of those aha moments. We've got some amazing material today.
We do. There's that incredible 20-year time-lapse of stars whipping around Sagittarius A, the supermassive black hole at our Galaxy Center.
Yeah, that Reddit post was stunning. And the first actual image of Sagittarius A from the Event Horizon Telescope. Plus, we'll get into dark matter, dark energy, how they link up with black holes and galaxy formation.
And finishing with blazers, those incredibly powerful jets shooting out from black holes.
Exactly. So our mission basically is to pull out the coolest insights, find the connections, and just revel in the sheer dynamism of it all. Ready to jump in?
Let's do it. Starting with Sagittarius A seems right, that time lapse. It really drives home how we see the black hole by its effect, even though it's, invisible itself. Predictably invisible.
Predictably invisible. I like that. You see those stars just looping around, and the speeds. Someone mentioned S4714 going at nearly 24,000 kilometers a second.
That's right, about 8% the speed of light. It's truly mind-bending velocity.
It makes you wonder, right? What would it even feel like on a planet orbiting something that fast, that close?
Well, that's where relativity comes in, but also just basic physics.
Yeah.
On the planet itself, assuming a constant speed, you might not feel the speed directly, but what you would feel is the acceleration. Especially for a star like S4714, its orbit isn't a nice perfect circle. It's highly elliptical, really stretched out.
So it speeds up and slows down dramatically.
Exactly. It slows way down when it's farthest away, then it gets yanked back and absolutely whips around the black hole at its closest approach. That acceleration that you'd feel, it would be intense.
Cosmic slingshot. Wow.
And from an outside perspective, things get even weirder. Relativistic effects, time dilation, length contraction. For someone on that hypothetical planet looking out, the rest of the universe would appear to speed up and slow down, distort.
Wild. So Sagittarius A is mostly quiet now, gravitationally dominant but dormant?
Mostly. But it does occasionally snack on things that get too close a star, a gas cloud.
And when that happens, it's not so quiet anymore.
Not at all. The energy release is immense. The comparison in the source to staring into the LHC beam gives you an idea. Extreme radiation.
Yeah, definitely not a friendly neighborhood during feeding time. But it's interesting how stable those stellar orbits seem, despite all the other stars nearby. Isn't there a three-body problem where things get chaotic?
There is, but the key here is the sheer mass difference. Sagittarius A is so dominant, millions of times the mass of the Sun, that it largely dictates the orbits of the stars close to it. The interactions between the stars are minor compared to the black hole's pull. It brings a degree of stability to the chaos.
Okay, so the big boss keeps things mostly in line. But habitability. I mean, even without it actively feeding, the radiation environment near a supermassive black hole must be pretty harsh.
Extremely harsh. Intense radiation, powerful tidal forces that would shred planets. It's generally considered one of the least likely places for life as we know it. The discussion reflected that.
Right. Something else cool in that time lapse was seeing the image quality improve over 20 years.
Oh, yeah, definitely. That's adaptive optics in action. It's technology on our ground-based telescopes that corrects for the blurring caused by Earth's atmosphere. You can literally see our view getting sharper over time.
It's like the universe is slowly coming into focus. And someone pointed out weird little blips or distortions around some foreground stars in the video. Maybe energetic particles. Or lensing.
It could be. There are still little mysteries even in data like this. It shows we're always learning, always finding new questions. The sheer scale, though, it's humbling.
Definitely humbling. And, speaking of mysteries, the thread even mentioned people who are skeptical black holes even exist.
Right, though the counter-argument, especially now with direct images, is pretty strong. It's not like blurry photos of Bigfoot anymore. We have data points, orbital mechanics, images of the accretion disk.
Which brings us perfectly to that first image of Sagittarius A from the Event Horizon Telescope. After talking about its invisibility, we finally got a picture. Sort of.
Exactly. We don't see the black hole itself, the event horizon. What we see is its shadow silhouetted against the incredibly hot, bright material swirling around it, the accretion disk.
The cosmic drain pipe, glowing hot.
Precisely. Gas and dust get pulled in, compressed, heated to millions of degrees by friction and gravity, and they radiate energy like crazy. That's the light the EHT captured.
And this disk only exists if stuff is actually falling in, right?
Correct. If XGRA was completely starved, truly dormant, there'd be no glowing disk. We'd only know it was there from those stellar orbits we discussed. So the image confirms it is currently accreting some material, even if it's not in a highly active phase.
Okay, connecting the dots. Now let's shift gears a bit into the really weird stuff. Dark matter and dark energy. How do they fit into this picture with black holes?
This is where things get even more, well, mysterious. The VIX resources mention this puzzling link. The amount of dark matter in a galaxy seems tightly correlated with the size of its central supermassive black hole.
Wait, how? They're on totally different scales, aren't they? One's the whole galaxy's invisible structure, the other's the tiny point at the center.
That's the puzzle. Why should the galaxy-wide dark matter halo know how big the central black hole should be, or vice versa? It suggests a deep connection we don't fully grasp.
Is there any theory on how that might work?
One idea floated in the excerpts is pretty speculative, but interesting. It imagines dark matter having both matter and antimatter forms. If these particles accumulated inside stars over cosmic time, they could potentially annihilate, release energy, destabilize the star, and maybe trigger its collapse into a black hole.
Whoa! So dark matter could actually seed black hole formation.
It's one hypothesis linking them directly. It's quite out there, but it tries to bridge that scale gap. The sources also touch on how dark energy changed our view of the universe's fate.
Right, it wasn't just the big freeze or big crunch anymore. Dark energy is pushing everything apart, accelerating the expansion.
Exactly. And there's even a newer, more speculative idea mentioned that over truly vast timescales, dark energy might somehow swallow up dark matter. It hints at a dynamic interaction between these two dominant, invisible components of the universe.
Dark energy eating dark matter. Sounds intense. But remind us, these are inferred, right? We don't see them directly.
Correct. Dark matter's gravity holds galaxies together, bends light. Dark energy drives the accelerating expansion. Together, they make up something like 95% of the universe's energy density. Ordinary matter, stars, us. We're only about 4 or 5%.
Just a sliver. The excerpts also mention asymmetric dark matter, potentially causing pulsars near the galactic center to collapse into black holes, making them doubly invisible.
Yes, another theoretical idea. If certain types of dark matter interact with neutron stars, they could trigger collapse. But it's crucial to add that standard astrophysics might still explain why we don't see as many pulsars there as expected. We don't necessarily need exotic dark matter explanations yet.
Okay, noted. But the idea that dark matter is densest at the galactic core makes it a plausible place for any dark matter interactions to be most significant.
True. Now, let's link this back to the galaxies themselves. Black holes aren't just sitting there, they actively shape their host galaxies. The Royal Observatory Edinburgh material really digs into this.
They're not passive residents, they're architects. Or maybe regulators.
Regulators is a good word. When supermassive black holes actively feed becoming active galactic nuclei, or AGN, they blast out enormous amounts of energy. Radiation, jets.
The stuff we see in blazars sometimes.
Exactly. And even a small fraction of that energy is enough to heat up the gas in the galaxy's central bulge, or even blow it right out of the galaxy.
So it stops that gas from cooling and forming new stars.
Precisely. It's called AGN feedback. It can effectively shut down or throttle star formation, especially in the central regions. It acts like a thermostat for the galaxy.
A cosmic thermostat. I like that. And this happens in the context of those giant dark matter halos that galaxies live in.
Yes. Galaxies form as gas cools within those dark matter halos and settles into disks where stars are born. But there seems to be a critical halo mass around 1 trillion solar masses. Beyond that, the AGN feedback becomes efficient enough to prevent much more gas from cooling and falling in, limiting the galaxy's growth.
So the black hole's feedback sets an upper limit on how big the galaxy can get, or at least how many stars it can form.
Largely, yes, especially for the most massive galaxies. Mergers between galaxies also play a role, often transforming star-forming disks into more bulge-dominated elliptical galaxies where feedback might be more dominant.
Okay. Does this help explain things like the cooling flow problem? I remember reading about that.
It's central to it. In big galaxy clusters and giant elliptical galaxies, there's tons of incredibly hot gas that should be radiating energy away, cooling rapidly and forming stars like crazy. But often we don't see nearly that much star formation.
The gas is there, but the stars aren't lighting up, so the AGN feedback is the heat source stopping the cooling.
That's the leading explanation. The energy injected by the central black hole's jets and radiation balances out the radiative cooling, keeping the gas too hot to collapse and form stars.
It's like heating the room so the condensation doesn't form.
A very good analogy. Quasar winds, powerful outflows from the AGN, might even preheat gas before it falls into the cluster. The jets inflate huge bubbles or cavities in the hot gas, drive shock waves. It's a very energetic process.
And even when the black hole isn't actively having a huge feast, the remnants of past jets, those radio loads, can still contribute.
They can. As these bubbles of relativistic plasma rise buoyantly through the cluster gas, they stir it up, creating turbulence that dissipates as heat. They can also physically lift cooler gas from the center, preventing it from cooling further.
It's this incredibly complex, ongoing balancing act. The sources mention correlations, right, between radioactivity, black hole mass, and gas cooling rates.
Yes, there are observed scaling relations that strongly support this feedback loop idea. More massive black holes and ellipticals are more likely to host radio jets, and this activity correlates with how fast the gas should be cooling.
But it's complicated to model perfectly.
Extremely. We rely heavily on computer simulations, and accurately modeling things like star formation efficiency or the detailed physics of the interstellar medium within those simulations is still a major challenge. The basic picture seems right, but the details are still being refined.
Always more to learn.
Which brings us nicely to those jets themselves and blazars.
Right. Blazars are basically AGN, where we happen to be looking almost directly down the barrel of one of those relativistic jets. So it's all about the viewing angle.
Largely, yes. That specific alignment dramatically boosts the radiation we see because of relativistic effects. Doppler boosting, beaming, it makes the jet appear incredibly bright, often outshining the entire host galaxy.
Like looking straight into a cosmic headlight.
Yeah.
What's the basic setup again? Black hole, disk.
Supermassive black hole at the center, accretion disk feeding it, often a dusty torus further out, and then these powerful jets shooting out from the poles, perpendicular to the disk, at near light speed. The IAA CSEC material and figures illustrate this well. That M87 jet image is a classic example.
And how these jets get accelerated to near light speed and stay so tightly focused? That's still a bit of a mystery.
The big mystery. We know magnetic fields are involved, likely extracting rotational energy from the black hole or the accretion disk, but the exact plasma physics is incredibly complex and hard to observe directly.
We see the result, not the engine room. What about the light they emit? Synchrotron something.
Synchrotron radiation, yes. That's generally accepted as the source of the lower energy emission, radio through maybe X-rays. It's from electrons spiraling in the jet's magnetic fields at relativistic speeds.
Okay, that makes sense. But the really high energy stuff, the gamma rays.
That's more debated. The leading idea involves inverse Compton scattering. Those same relativistic electrons collide with lower energy photons and kick them up to gamma ray energies.
Like a superpowered billiard shot. But what photons are they hitting?
That's the main question. Two main scenarios. Synchrotron self-Compton, SSC, where the electrons scatter the synchrotron photons they just emitted, or external Compton, EC, where they scatter photons from outside the jet, maybe from the accretion disk, the dusty torus, or even the cosmic microwave background.
So using their own light or borrowing from the neighborhood?
Pretty much. Observing across the whole spectrum helps distinguish these models. The sources also mention things like Doppler boosting, making one side of a jet appear brighter.
Right, because it's moving towards us.
An apparent superluminal motion. Features in the jet can look like they're moving faster than light because of the viewing angle and relativistic effects. It's an optical illusion, but a consequence of the extreme physics. VLBI lets us track these features.
Mind-bending stuff. The sources also touched on pair production, gamma rays making matter.
Yes, a very high-energy gamma rays can interact with lower-energy background photons, like the extragalactic background light, and convert their energy into an electron-positron pair. This can affect how many gamma rays actually reach us from distant blazars, and the Eddington limit is mentioned too.
That's the theoretical speed limit for how fast a black hole can eat.
Sort of, yeah. It's the maximum luminosity an object can have when gravity pulling material in is balanced by radiation pressure pushing it out. It sets a kind of limit on how bright an accreting black hole can stably be.
It's clear you need observations across all wavelengths, radio, optical, X-ray, gamma ray, to piece together what's happening in these incredibly energetic objects.
Absolutely. The detailed study of the Blazar AO0235 plus 164 mentioned in the excerpts is a perfect example tracking flares and changes across the spectrum to understand the underlying physics. It really showcases the complexity and how different processes are linked.
It's amazing how we can build these pictures from light that's traveled for millions or billions of years.
It really is, and what stands out is how interconnected everything is. The stars orbiting the black hole, the dark matter shaping the galaxy, the black hole regulating star formation with its feedback, these powerful jets. It's all part of one grand, dynamic, cosmic dance.
A truly breathtaking spectacle. Well, learner, that brings us towards the end of this deep dive with the All Sorts podcast. We really hope this journey through black holes, galaxies, and jets sparked some curiosity, maybe give you a few of those aha moments.
The universe is just endlessly fascinating, isn't it? There's always more to uncover.
There really is. And as you ponder the sheer scale and energy we've talked about, we'd love for you to join our community here at the All Sorts podcast. If you enjoyed this cosmic exploration, please do us a huge favor, like, share, and subscribe to the All Sorts podcast on YouTube.
It really helps us keep these deep dives going, and you can find plenty more fascinating topics in our previous deep dives wherever you listen to podcasts.
That's right. And stay connected with us for future insights and discussions. Follow the All Sorts podcast on X, Instagram, and Threads. Just search for All Sorts podcast, nice and easy. Every click helps us explore more wonders for you.
So here's a final thought to leave you with. We've seen these seemingly separate pieces: star orbits, dark matter, AGN feedback, galaxy evolution, relativistic jets. How might they be connected even more deeply in ways we haven't even figured out yet within this vast cosmic dance?